Okay, so today we're going to continue with the final review and go through the Emporium model where I do a problem and then you solve a similar one. And what I'm doing, I'm picking ones that are directly, the concepts are directly on the final. So it's not like, although the final, it's 70 questions, multiple choice, short questions. Like I remember we did one on with the linear reagent percent yield. That's like, questions aren't that long. It's a simple one like, what's the limiting reagent? Another one will be, what's the theoretical yield? Another one, what's the percent yield? But they will be quickly done, something you can do in a minute or two. But I'm going over the lot with the review. But okay, but there is a problem like this. So, titration problem. 25 milliliters sample of unknown perchloric acid solution our solution requires titration with 22.62 milliliters of 0.2 molar sodium hydroxide. What's the concentration of the unknown HCl4 perchloric acid solution? So when you do these, the idea is that the moles acid equals the moles of base. But let me go ahead and you can also solve with dimensional analysis. So the way you do that, it would be 0.2 moles NaOH per liter times 0.02262 liters, and then mole HClO4 to mole NaOH, and then it's a concentration 0.025 liters. So if you see what's happening here with dimensional analysis, so the 0.2 moles sodium hydroxide per liter, 0.2 molar, and liters cancel, so now you get moles sodium hydroxide, and then 1 mole perchloric per mole sodium hydroxide, and you get that from the balanced equation here. And then just divide by, so at this point in time you're getting moles perchloric acid, and then divide by 0.025. That's the volume, the 25 milliliter, and that gives you the concentration. So going left, right, this way always works. You can also do the moles acid equals moles base, although I am doing it like that way with the dimensional analysis. But that way you would think, okay, I'm going to calculate the moles of sodium hydroxide, then that's the moles of perchloric, and then once I get the moles of perchloric, then I divide by the volume to get the molarity. So either way that you prefer, 0.2 times 0.02262 divided by 0.025. And this equals 0.18 molar HClO4. The other answer is, does this make sense? And I think it does, because so we needed 22 milliliters of 0.2 molar sodium hydroxide, and then to titrate 25 milliliters. That means the concentration of perchloric is going to be less than 0.2. So but not that much less. So this answer makes sense. So, all right. So you guys try number 90, and I'll be around. Is anybody stuck? I have no idea what to do. No? Okay. So start working on it, and I'll come around and help you out. Oh, you're right. There's 3. You do it. Oh, yeah. Yeah. Got it? There's an issue that we have. Oh, that's the first one. Yeah. The thing is that this one, it's a 1-to-3 ratio. So 1-to-3. Yep. All right, good. So people are getting that. Anybody have any questions on how to do this? Okay, assign oxidation states. So if you remember the given information, you guys got the given information I passed out, right? Okay. So you do not need to print that out. I will provide you with a copy. And in that given information is this. These rules for having oxidation states. So you will be given this information on the test and assign things oxidation states. So for the first one, A, this is rule number 1. If you can, I don't know if you can read that there. The oxidation state of a free element is 0. So silver right here is 0. The next one, number 2, is a monatomic ion equals its charge. This one's +1. And then for part C, it says the sum, for rule 3, the sum of oxidation states in a neutral molecular formula unit is 0. That works for this one here. So that means calcium's oxidation state, calcium's oxidation state plus 2 times fluorine's equals 0. And if you look then at rule number 4, 2A, that's alkaline earths, they tend to be +2. They always are +2. So calcium is going to be +2. And if calcium is +2, that means fluorine is forced to be -1 for that to be 4. So, because if you have 2 plus 2x equals 0, x equals -1. So fluorine is -1. How are we doing so far? Any questions with this? Okay, same idea for hydrogen sulfide. So you have hydrogen, 2 hydrogens plus sulfur equals 0. And that's rule number 3. Keep on going down rule number 4. And these rules are hierarchical, meaning 1 is more important than 2, then 3, then 4. And then we have to go to this chart. And you can see hydrogen tends to be +1. So we put in then 2 times +1 plus sulfur's oxidation state equals 0, and sulfur is -2. Like that. So this is +1, -2. Questions with this one? Okay, so the next one, the rule number 3, an ion is the sum of all oxidation states of an ion is equal to the charge of the ion. So this next one here is an ion. Actually, E and F are. So so carbon plus 3 times oxygen equals -2. So do you see that? That's C. 1 carbon, 3 oxygens is equal to -2. And then following the rules on the chart, oxygen tends to be -2. So carbon plus 3 times -2 equals -2. And carbon, so 3 times -2 is -6. 6 on both sides, -2 plus 6 is +4. So carbon here is +4 and oxygen is -2. And then the last one, same rule. Chromium plus 4 oxygens equals -2. Oxygen tends to be -2 plus 4 times -2 equals -2. 4 times -2 is -8. 8 on both sides. Chromium equals 6. So that means chromium is +6, oxygen is -2. So, how are we doing so far? Anybody have any questions with this? I'm going to move this one down. Let me do this. All right, your turn. Let me blow this thing up. So. So assign oxidation states to each of these. Is anybody stuck? In that case, I'm going to eat an apple. Oh, and please, pretty please, fill out the evaluations for this class. I'm giving you extra credit to do it. Also, for the final, I bought 3 pounds of chocolate. So hopefully 3 pounds of chocolate will be enough. You guys seem much more excited about the chocolate than you were about the course evaluations. I'm disappointed. Yeah, I know it's hard to read, but I mean, it'll be much more clear when you can test. Are you going to take it with me or are you going to do it?
Oh yeah, but it is too nasty.
Okay. Okay. Whatever you prefer. Maybe. Yeah. Sure, send me an email. Yeah. And I can also set you up a phone if you change your mind. Let's do this. That just doesn't matter. Because I mean, there are also advantages to have taken care of. The other thing is the brain drain. I mean, if you're going to take my test and then calculus, I mean, that's just a big brain drain. That's 6 hours of thinking. So, in your shoes, I probably would take the test. Just less of the thinking systems. Yeah, so just, I'll also, I can answer questions. Answer questions like, say it says fluorine and there's a CL or CL2. For some reason, we forget that church. And I won't answer a strategy question. Unless, what do I have to use number 3 or number 4? I wouldn't answer that because that's a strategy question. Definition question. What is this? What does this mean? That's the answer. They're meant to be limited less. Like the ones that we were taking, they were much harder. Yeah, so it's not like the chance to I think 70 questions would take you plus 5 hours. Yeah. So it's designed to be done. Yeah. That's also too.
What's the charge of
This one, so it's also the one where that would be -2, sulfur plus 1 is -2, so that's -8. So sulfur -8 is -2, and sulfur is +6. No, that's alright. The setup is right.
Oh, this is not.
Boom. Okay. Keeping the chart in mind, determine whether each reaction is a oxidation reduction reaction. Redox is reduction oxidation, oxidation reduction. For each redox reaction, identify the oxidizing reagent and reducing agent. So an easy way that will always work is to get the oxidation states for each one. So lithium is 0, oxygen is 0, lithium becomes +1, oxygen becomes -2. This is an oxidation reduction reaction, and then so the oxidizing agent and reducing agent, the oxidizing agent is the one that causes the oxidation, it's the one that's reduced, and the reducing agent is the one that's oxidized. I know it's backwards. The reducing agent causes the reduction. How does it do that? It gives off the electrons. By giving off electrons, it's oxidized. So lithium is the reducing agent. And then oxygen is the oxidizing agent. And oxygen is also the most common oxidizing agent. So part B, magnesium is 0, iron is +2, goes magnesium +2, iron 0. This is an oxidation reduction. Written the same way, magnesium is being oxidized, therefore it's the reducing agent. And then iron +2 is the oxidizing agent. Okay, so lead is +2, and the other thing, if you look at the nitrate and the sulfate, they're not changing. You can pretty much just ignore them. So just look at the metals. So lead is +2, sodium is +1. Lead is still +2, sodium is still +1. There's no electron transfer. This is not a oxidation reduction reaction. Then here, HBr, hydrogen's +1, bromine -1, potassium +1, oxygen -2, hydrogen +1, water, hydrogen still +1, oxygen still -2. potassium plus, bromine minus. No electrons transfer. This is not an oxidation reduction reaction. So just the first two are. So this is one of two sets of problems. One is to identify an oxidation reduction reaction. The other one is to identify like a oxidizing agent or reducing agent. So you do have to know how to do this. So remember that reducing agent is the one that causes reduction. It's the one that gets oxidized. Reducing agent gives off electrons. The act of giving off electrons makes it oxidized. Oxidizing agent rips off electrons. By ripping off electrons, it becomes reduced. So, and anybody have any questions with that? All right, so let me, you probably want the chart. Let me move the chart down. Actually, maybe I can do this. Copy it. But no. Where'd it go? Sorry. Okay, I think the memory's getting too full on this sucker. No. Sorry about the... Sorry, the memory is getting too full on this and it's moving too slowly. Can you read that? Okay. Anyways. All right. I'll just go ahead and give you the oxidation states since you've already proven you can do that. Sorry, I didn't get lunch because lab ran late, so I need fuel.
it's yeah, aluminum 0 plus 3. So oxidized. Silver plus 1 is 0 is being lost. Aluminum's giving electrons to silver. So aluminum is being oxidized, silver's giving since aluminum is losing electrons, it's the reducing agent. Silver is gaining electrons, it's oxidizing. What this one means. Now the numbers change. So, yeah, sulfur 6, here, oxygen -2, here, here. Hydrogen is +1, +1. So, yeah. Yeah. It's always -2. Yeah, it's not gaining any electrons. Yep. You got it. I mean, this is so for part B, sulfur is 6 here and 6 here. Oxygen -2 here, -2 here. Hydrogen is +1 here, +1 here. And there is the change. So this is the object. And then here, barium, chlorine, and starting with barium, so this is 2 electrons. So this is this is barium is being oxidized. This barium is reducing agent. Yeah, just chlorine trying to this causing oxidation. It's being reduced, it's causing this to be oxidized. It's oxidized, it's causing this to be reduced. Okay. Try to look for lucky. Fifty. No, it's think of it the opposite. So bromine being reduced. So it's
causing you to be oxidized. So this is an electron. I'm an oxidized because now oxidized. I'm being reduced, but cause you to be oxidized. Now, if I do this, you're reduced. You have an electron. But I'm the reducing agent. Even though I saw myself, I lost. So I'm causing you to be reduced. So I get oxidized. Likewise. Now I'm the oxidizing agent. Reduced because I grabbed the electron. I mean, it's kind of backwards logic, but yes. And B is no red, is not a yeah. Actually, no, it's backwards. Aluminum is the oxide, silver is the oxide. Yes, it's here. Because aluminum is losing silver is gaining oxide. Aluminum is reducing cool. Now, like James Bond, go read that. Arnold Schwarzenegger, Terminator. Cheers. Give me the That's right, that's right. So that's right, except for B is not. So it's just well, it is something. It's a it's how it's a good reaction. It's sulfur plus 6 here, plus 6 here. Oxygen is -2 here. This is called combination. These two things are combined in one element. This is it's non-oxygen. Yeah. If one of them changes, yeah. If one of the two or more species, two more atoms change their operation. Okay. So now we're on to chapter 5. Hooray! Okay. Does anybody have any questions with that before we move on? So you will get this on your equation sheet, but the RMS velocity is, oh wait, actually, it's 3RT over molecular weight, and M is in kilograms, but so, okay. Rank these three in terms of diffusion. So the lighter one is going to fuse faster, and the heavier one will fuse slower. So, and so the masses, so this is fluorine. This is going to be 38 grams per mole. Chlorine is going to be 70.9. And bromine, what is it, 70, is it 79.9? Just broke this. 79.9, so that's 159.8. So this is 159.8. So we have fluorine at 38 grams per mole, chlorine at 70.9 grams per mole, and bromine at 159.8 grams per mole. So in terms of a fusion, fluorine is going to be greater than chlorine, greater than bromine. So it goes by mass. And because of this, and the reason for that is root mean squared velocity is 3RT over m molecular weight. The same temperature, R is a constant, so that's the same. The molecular weights change, and the lighter one, the smaller m is divided by n, the smaller number here is going to give the bigger number overall. So fluorine the lightest, it'll diffuse the fastest, then chlorine, then bromine. So let's see what you think about the next ones. Carbon's 12, oxygen 16. Sulfur's 32.06, but I'm not going to, whatever. Oh, I'm supposed to calculate the root mean squared velocity. I'm sorry, I should do that for one of them. I'll do it for fluorine. And just calculate the root mean squared velocity for carbon monoxide, because you don't have to do them all for all. That would take too long. And on the given sheet, you're given the equation and, and the fact that m is in kilograms. Oops, should be started. Yep, you got it.
Zero to 8. That's all. Gas cost? This, it has to be on the units. This makes you have to use the 3.4. So like the chapter 5 stuff, lots of people use it for 0.08206. That's for liter, that's for Kelvin. This is joules per mole Kelvin.
Well, I was using the wrong value I have no idea how to do that.
You say 0.314?
No, I was using point.
Yeah, that's the reps. If you look at the units, so joules per mole Kelvin times Kelvin divided by kilograms. So kilograms.
Yeah, just like you just
So sorry, I'm writing too small. Do you know what the unit bonus for the class? Here's the reason why. It's joules per mole Kelvin. So the Kelvin's cancel. So yeah, joules per kilogram. A joule is a newton meter. It's a kilogram meter squared per second. So kilograms cancel when you're left with the square root of meter squared per second squared versus meter per second. So that's the reason why you use units. Sorry, that's a little stuff from chapter 5. So, that'll be, and you did both the tests, so I forgot it all, but that's okay. It's easy to do right now.
Yeah.
That's why I'm doing this. Are you following?
Yeah, I just want to know if I'm plugging in.
We'll put no, 0.028.
Well, yeah, but okay, this one.
That's 28 is grams per minute. That's it. Did you sort it?
Oh, okay.
like
Yeah. So C will be the fastest. So 3D.
She's just trying to make you jealous of
Yeah, that's fine. But the views and units are.
So the units I'm just trying to.
Yeah, it's acceleration, so force is mass times acceleration. Acceleration is singular position. So mass is space, mass times length, times the acceleration is it's the second. So it's distance divided by square root of acceleration. Force is mass times acceleration. Displacement divided by time squared. And that's force. Actually, scared. So that's a force. That's 1 meter squared. A joule is the force of 1 newton over 1 kilometer. So it's a meter. So it's kilogram meter squared.
I'm assuming Oscar helped you guys. So. Okay, so this graph here shows molecular velocities, two different molecules, same temperature. Which one has the higher molar mass? Which one has a higher rate of fusion? So the heavier molecules have a narrow distribution. The lighter ones have a broader distribution. So A is heavy, B is light. So that means A has the greatest lower molar mass, B has the lower molar mass, B also effuses faster, A effuses more slowly. Does that make sense? Okay. And here, molecular velocities, same one. Which one has the higher temperature? So same molecule, different temperatures. The cooler temperatures are more narrow and they're closer to 0. The higher temperatures are more broad and the root mean squared. So remember the root mean squared velocity is this peak. So the higher temperature means it's moving faster. So this T2, the average velocity is here. It's higher than T1. So, and higher temperature means higher velocity. T2 is greater than T1. So you can tell that also the distribution. The high temperatures are more broad and the peaks further out. The lower temperatures are more narrow. The peaks closer in. So, make sense? So as you can tell, I hope you get that because questions like this are on the final. So anybody have any questions with this? Okay. although maybe a little redundant, going over stoichiometry, but with gases. How many liters of hydrogen gas are formed by the complete reaction of 15.7 grams carbon? So for this one here, it is a limiting reagent problem, although you're told what the limiting reagent is. So 15.7 grams carbon times mole carbon to 12 grams carbon. So mole hydrogen to mole carbon, and we stop there. So this is 1.31 moles H2 equals NH2. And the second part of this, assume the hydrogen is collected at pressure of 1 atmosphere, temperature of 355 Kelvin. So this asks for liters. So PV equals nRT. Solve for V. V is nRT over P. 1.31, which we just solved. 0.08 0.08206 liter atmosphere mole Kelvin, temperature 355 Kelvin, all over 1 atmosphere. And this is 38.1 liters. So, all right, try 72 then. Although that's a little bit backwards. So 72 is a little backwards. You're asking for the mass of water, 1.4 liters of oxygen at temperature 315 Kelvin and 0.957 atmospheres. Solve for N, so N equals PV over RT. Solve for N for oxygen, and then you're going to need twice as many moles of water as your oxygen, and then multiply that by 18 grams per mole to get you the mass. Oh man, I'm losing so much energy. I should eat when I teach more often. I mean, there's no eating in this classroom, so clearly I'm not eating YouTube. I record the lectures.
Is it the mole 0.05, 0.052, 0.5?
Okay, dreaded Hess's law. So calculate Fe2O3 plus 3CO makes 2Fe plus 3CO2 using these ratios. So I'm just going to call this H1, call this one H2. And when you do this, make sure that the reactants are on the left and the products on the right. This first equation, Fe2O3 is a reactant, so I need to flip this one here. I'm going to keep the same because CO is a reactant and CO2 is a product. So for 79, I'm going to flip this one. Fe2O3 goes to 2 iron plus 3 halves O2, and this is minus H1. And then we have CO plus 1/2 O2 makes CO2. And we'll just leave this as H2. But we need to have 3 times as much CO2. So I'm going to multiply it by 3. And then I can add these together. And the 3 halves O2's cancel. And I get Fe2O3 plus 3CO makes 2Fe plus 3CO2 minus H1 plus 3H2, whatever the heck that is. And let's just do that now. We can just stop there. And we have 4 minutes left. Then for you to do 80. So let's just get to so the first equation, calcium going to calcium carbonate. Calcium carbonate is a product that's on the right. You leave that as is. Second equation, calcium oxide solid is on the wrong side. You have to flip that one. And there is only one of these on the final, and I consider this an easy one. These are easy ones. I don't know if you consider these easy. Students usually hate Hess's law. Although I know I'm running out of time, I got less than 2 minutes. So, but I am hoping that you see that you do not alter the first equation because calcium carbonates and CO2 is on the left side, calcium carbonates on the right. You leave this one written as is. This other one, calcium oxide, is on the wrong side, so you have to flip it. And also, after you flip it, you should divide it by 2, because so when you divide it by 2, you get the right amounts. When you add these together, first of all, the calciums cancel, so you get rid of the calciums, you divide it by 2, and the half the oxygen cancels. You get the calcium oxide plus CO2 makes CaCO3. It's the first heat minus the second heat divided by 2. So that's the overall equation, whatever those numbers end up being. Does that make sense? Come talk to me if you need more clarifications on those. But also keep in mind it's only one question. So, okay, class is over unless you want to talk. Oh, class is over. That's a shut up alarm. Otherwise, I'll forget. And we're doing the same thing on Wednesday if you want to come. Now we're noon or 3 p.m. Where do you live? Okay, so that's moderate drive. But
Yeah.
yeah.